Thanks very much. My talk is going to be really different from the ones you've heard this morning because I'm going to talk more about the past than the future. I'm going to talk about abstraction and how the use of abstraction in designing and implementing programs came about. So, as all of you in the room know, it's not easy to design and implement large software systems because software is really complicated. We build really big systems, millions of lines of code, and our systems do complicated things, and furthermore, they often do things that they haven't done before, which makes it much harder to design them than if they're similar to what we've done already. And of course, to make things even worse, they might be distributed, they might be concurrent, which makes it even more difficult. So addressing complexity has been a core issue in research in computer science, and one place where tremendous progress has been made is in the area of algorithms, data structures, and protocols. When I started out as a programmer, if you wanted to build an efficient data structure to do something or other, searching or whatever, you had to invent it yourself. They just didn't exist the way they do today. Today, you go to a book, you read about B trees and hash tables, or even better, you look in the library of your programming language and they're already there ready for you to use. But that was not true at the time. And this is due to work mostly in theoretical and computer science, but also in networking and so on. However, wonderful as all this stuff is, it doesn't really get to the core of the issue, which is how do you design the programs in the first place? You can't decide that you need a data structure that does X until you've figured out that having such a thing is an important piece of your program. And in order to do that, you have to design. And that has been the topic of work in programming methodology. And then as program methodology has occasionally come up with some idea that could then be incorporated into a programming language, sometimes research in programming languages follows on. I'm going to talk today about how the programming methodology as we understand it today developed, and a little bit about how it moved into programming languages, and I'll end it with a few ideas about future research, much more focused in the near term than the far term at the end. Okay, I started working in programming methodology in 1970. So what happened to me after I was rejected by Princeton, and then I was looking for a PhD in mathematics, I ended up in computer science. I went to Stanford. I got my PhD in AI. I knew partway through my graduate career that I really didn't want to work in AI. The reason was I thought it was too hard. I wanted to do work in machine learning. In those days, in machine learning, the idea was that machines would learn just the way people learn. This really didn't work very well, and as those of you who are in AI know, things have really changed in the last 20 years. Anyway, I felt I had no intuition about how to make progress there, and I was much more interested in systems. When I got my PhD, no universities wanted to hire me, and I got a job at the MITRE Corporation working in a research position. And as soon as I got that job, I switched from AI to computer systems. And the first project I did there was to build a little multi-programming system. This was the time when that was really a new topic. And after that, I was asked to work on the software crisis. Now, I was working at the MITRE Corporation, which is a company that works primarily on research that's asked for by the government, the US government. They send out what's called an RFP, a request for proposals. MITRE might respond to one of these saying, we're going to do some research on this particular project that you're interested in. And in 1970, the government was very worried about what was called the software crisis. And what the software crisis was that people were building big programs that didn't work. So they might sink millions of dollars, hundreds of man-years into some program that they were trying to get to work. In the end, they'd have to throw the whole thing away. And actually, stories about these crises, these horrible disasters, continued right through the 80s. So it wasn't uncommon. You'd pick up, a story about, London was going to have some system that would let the ambulances to the right places, and they spent all this money. In the end, the system didn't work. They had to throw it away. So the government was very concerned about this because they had very ambitious software systems in mind, and they didn't know how to build them. And they asked MITRE to see if they could come up with a solution, and MITRE asked me to work on the problem. So I did what any sensible person does when they get into a field they haven't worked in before. I read the literature. And I'm going to tell you a little bit about some of the papers I read. And when I got the Turing Award, I went back and reread these papers, and it was really great. I mean, these are really good papers. If you haven't read them, I suggest that you do. Before I talk about the papers, I just want to point out that program methodology is actually about two separate but related topics. One of them is about how do you do design, how do you organize your thinking, come up with a design, a structure that's going to work for your software system. The second one is what should structure look like? So the two are sort of interrelated. If you have some idea how structure should look like, this will help you in the design process. And work in program methodology has addressed both. Okay, the first paper I want to talk about, this is about program structure, a very famous, actually not paper, but just a letter to the editor of the communications of the ACM, only about 3 pages long, by Dijkstra, in which he said the go-to statement's a bad idea. Hugely controversial at the time. Today it may seem like, how could this have been controversial? I mean, after all the programming languages we use don't have go-to statements. Clearly, the go-to statement's not important, went away, At the time, of course, this wasn't true. People were writing programs in Fortran. They were writing programs in Algol 60. They were writing programs in programming languages that had go-to statements, and they seemed pretty fundamental to the programming model. So this was very controversial, and I think there were 2 main reasons for it. One was people felt insulted. So Dijkstra was really saying, these are bad programs, okay? And they were saying, I write programs using go-to statements, and they're good programs. And that might have been true, because if you're disciplined, it doesn't really matter what the programming language is. You can superimpose the discipline on your code and write a really good program, even if the language is terrible. The other reason is people were really concerned about whether the loss of the go-to statement would be such a serious matter that you couldn't write efficient programs in its absence. And in those days, programming languages didn't have the kinds of control structures that we're familiar with today, or some of them were lacking. And in the absence of these control structures, go-tos are a pretty useful item. Now, what Dijkstra said in this paper, intellectually, was a very interesting statement, and it was very early in the day for what was going on in computer science. He said, it's hard to reason about computer programs. In those days, in some sense, the software was sort of under the thumb of the hardware people, and there was a sense that software was trivial and all the real interest was in the hardware. They even made it worse because they would often buy, machines cost actual money. Programmers were kind of cheap. There was no real sense of how many programmers you would need in order to build some program. There was a tendency to trade off hardware for software, so they'd buy a cheaper machine, and the idea was the software could make up for it, so they made the problem even worse. So the software was an undervalued field. Dijkstra said it's an intellectually difficult activity to reason about the correctness of programs, and the reason for this is that when you reason about the correctness of programs, which after all is critical to getting a program that does what you're trying to get it to do, you reason about the program text. But what you're actually reasoning about is how the program behaves when it runs. So you're reasoning from something static about something dynamic, and he said, in order to make this as easy as possible, it's a good idea to make the two as close together as you can make them. And if you use well-structured control structures like if statements, whiles, recursion, and so forth, then they are relatively close together. If you don't, then they can be arbitrarily far apart. And if, for example, if you're debugging a particular place in your code, you're trying to figure out what went wrong. In order to do that, you have to figure out how you got where you are. That's relatively easy to do if you have well-structured control structures. It can be very difficult if you don't. And just one final point is people used to talk about programs then as bowls of spaghetti, by which they meant the control flow went all over the place. And when you have a program like that, it's a mess and very hard to reason about. The next paper is by Nicholas Wirth. This is a very different matter. This is about software design. And what Wirth said in this paper was, we're going to design programs from the top down. So you start with the problem statement. Then he said, you make a single design decision. Based on this design decision, you can then write what he referred to as an abstract program. Think just a sequence of comments. Okay, then you reason about this program. You think about it. You try to figure out, would this sequence of statements actually achieve what I'm trying to achieve? And when you're convinced that you do, then you select, he said, one or more, and you make a second design decision. Now we know today that design is not entirely top-down because obviously you have to worry about whether your program is going to run reasonably well on the hardware that you intend, and you might get down in the design process to discover there's some flaw in your reasoning. But if it's not primarily top-down, you have relatively little hope that in the end, the program's actually going to do what you want it to do. So design has to be primarily top-down. The third paper is a very famous paper by Dave Parnas. Dave actually wrote 2 papers on this topic at about the same time. And what Dave said in this paper is really telling. He said, programs are composed of modules. I don't know what a module is, he said. It's just a bunch of code in the middle of a bigger piece of code. But whatever a module is, he said, you need to sort of think about them independently, and in order to do that, you have to describe their connections, and the connections have to be complete. So the connections between modules are everything the modules assume about each other. That's that quote at the bottom of the screen. So this was a sort of a first step along the lines to what we think of as terms of modularity. So what I'm going to do now is talk about modularity from a more modern perspective. So we think about modularity today. This is how we build our programs. A program is a collection of modules. Okay, I'm not going to say yet exactly what they are, but each module has an interface, which today we would describe with a specification. We might write this just in English, but nevertheless we have a description of the behavior expected of this module. This is what Parnas meant by connections. If we have a specification, and furthermore, programs sort of stick to this methodology, then I can talk about whether a module's implementation is correct by simply talking about, does this module behave as its specification says it should? Now, in this module, I might make use of other modules. And to reason about those other modules that I'm using, I use their specifications. So what you get out of this is a way of breaking down a huge program into smaller modules, each of which can be thought about independently, which is a huge win. You know, a module might be 1,000 lines of code, something like that. You're talking about a program with millions of lines of code. You can't possibly understand millions of lines of code. But if you can break it down into pieces and reason about each piece independently, then you have some hope of understanding. An example of a module, a very simple one, is a sort routine. We understand that at the end, the array is sorted. We don't have to think about how we accomplish that. Okay, so modularity has huge benefits. And the first one is local reasoning, which is what I was just talking about. A second one is modifiability. This is sort of a secondary one, sometimes forgotten about. But modifiability is extremely important because what it means is that if I have a module that's doing what I want, but it's not doing it the way I want, it's not performing well enough, then I can rip out that implementation, replace it with a different implementation, as long as that satisfies the specification. And furthermore, everybody obeyed the rules. In other words, everybody was just using the specification. Then what I can end up with is a program that does correctly still the same thing, but it does it much faster. So this gives you a methodology for building systems where you don't try to focus on what's the most efficient performance right away, since usually you don't understand that in the beginning, but you have a way of getting there by pulling out pieces of modules and replacing them with better implementations where you need them. Okay, and then a third reason for modularity is independent development, because you can give different modules to different programmers. They can work on them independently. In the end, they will still fit together, provided they are all satisfying their specifications and assuming the specifications. I think this third point was the main reason people were using modularity back in 1970. Okay, so that's a modern understanding. What was the situation in 1970? Well, as Parnas says, I don't know what a module is. People sort of understood that procedures were modules, but they didn't understand what modules were in general. They were just these regions of code. And everybody understood that procedures really weren't powerful enough to be the kinds of modules that we needed. Because, for example, a file system is clearly a module in an operating system, but it's not a procedure, it's a bunch of stuff. And so, how do you connect that to procedures? And it's very important. Procedures were a powerful kind of module because they are linked to abstraction. A procedure is an abstract operation. You can think about it as what does it do? You don't have to think about how does it do it. But you need to be able to apply that to other things that are not procedures. In fact, when I started in this game, procedures weren't even used all that much. They were often used as a code shrinking device. So, you would say, well, here's a bunch of code, here's another piece of code. They kind of do the same thing. I could save space if I put them together, and then I could call them from two different places. Of course, I might need some extra arguments, so they got these horrible interfaces, so you'd have complicated connections. So that was the situation in 1970. People sort of knew the unit of modularity. They didn't really know what it meant. Okay. So I read these papers and a bunch of others that were also very good that I don't have time to talk about, and I realized I'd invented a methodology. Now, I did this not because I was thinking about programming methodology, but because I had a system to build. And I was worried about whether my small team of programmers could build this, what was a fairly sophisticated system at the time, a multi-programming system. And the way that people built programs at the time was every piece of code interacted through global state. So this was just sort of the norm for how you built programs. And it was kind of it was enforced even by the programming languages that existed. So, that was the day of Algol 60. Algol was a block-structured language. Now, a block-structured language says that in inner blocks, you can have some local state that other code can't touch. But on the other hand, it's perfectly okay for your inner blocks to communicate with one another through outer scopes. So that's a shared global state. And global state is it's a confusing way for programs to communicate. So what I decided in this project that I had done was that we wouldn't have any global state. I decided instead that we would write all the code up into what I called partitions. Each partition would own some subset of the global state, and the rest of the program could not interact with the state owned by some other partition except by calling its operations. So a partition provided a set of operations for use by the rest of the program, and inside it had some hidden local state that only it would manipulate. And we used this methodology to build our system. It worked quite well. And that was what I described in this paper. Okay, so now it's 1972, and I moved to MIT. Okay, so what happened was I had written up my previous project at MITRE, which was the Venus operating system, submitted to SOSP, which is the top systems conference. It was a prize paper. And Jerry Salzer, who was a professor at MIT, was my session chair, and he invited me to apply to MIT. What had actually happened in the United States was that they had passed a law called Title IX that talked about equal opportunity for women. It was mainly for athletics, but it was being applied more broadly. And as a result of this, some universities, and MIT was actually very forward-thinking here, were interested in hiring women, and so they were looking for women. And that's why Jerry Salzer thought to ask me to apply to MIT. And so I moved from MITRE to MIT in the fall of 1972. It was a really opportune time for me to move because working at MITRE, I would do this project and that project. A new RFP would come in, I would work on that. By the time I got to this stage in my career, I was really focused on methodology. There was no way I would have been happy leaving that topic and switching to something else. And one of the nice things about working at a university is you are in control of your fate. It's true that if you can't figure out how to convince somebody to fund it in the United States, you might go down in flames, but nevertheless, you can decide what you want to work on. You're your own boss. So I went to MIT and I was focusing on methodology. And I was really interested in the question of how could these ideas in these papers, including my own, be applied to building programs. What I had felt was you would read these papers, they were very convincing. They often had an example, you'd say, oh yes, I can see this is exactly the right way to solve this problem using these ideas. But when you tried to move away from that paper and that example to your own problem, it was really difficult to figure out what to do. And I think in retrospect it's because everything was so vague. There's sort of hand-wavy stuff. Anyway, I was really focused on this problem. And somehow, at some point, in either the fall of 1972 or early in the turn of the year in 1973, I had one of those moments that we all dream about, a sort of an aha moment, when all of a sudden I saw that data types and partitions could be the same thing. So if you think about it, let me see, connect partitions to data types, in retrospect, completely obvious. Completely obvious. You look at that partition, it's an object. It has a bunch of operations that you use to interact with it. Inside is its representation. But, at the time, it was not at all obvious. I read these papers afterwards, I can kind of see data abstraction lurking in the words, but nobody ever pulls it out. And as soon as I thought of this idea, I knew it was important because data types are an abstraction. They're sort of like procedures, except they're more powerful. And if you can link notions of modularity to notions of abstraction, then you have some hope of doing design. Because design, the way we design really is we abstract. We think of abstract things that if they were present, they would help us in building our program. And here's another really concrete idea about abstraction. Okay, so that was, sometime in 1972, 73. And then I started working with Steve Zyliss to try and take this vague notion that a partition and a data type might be the same thing to figuring out what is this abstract data type anyway. And Steve was a really good person for me to work with because he was an employee of IBM. He was also a graduate student at MIT. He had similar ideas about data abstraction, so we already had a meeting of the minds. He came from that IBM background, which in those days, IBM was the chief player in programming languages, so he was really well versed in all the programming languages. There was Fortran, PL1, and COBOL. I came from AI, I brought in my Lisp background. So Steve and I started to work together, and now we're really working on programming language design. And so, again, we started reading the literature. I'm not going to spend time on this because we're a little short on time for here, so I'll skip this one. But anyway, I reread several papers. Here's this paper. This is a paper on Simula 67. Okay, so what we're doing is we're reading papers on programming languages as it existed at the time. And one paper we read was about Simula 67. Simula 67 was extremely important programming language. And it was very influential in the development of programming languages. It's the whole small talk stream of languages came out of Simula 67, leading into object-oriented languages as we know them today. Simula 67 had classes and subclasses, so it had inheritance. And, so we could see that this was related, this notion of there's some state and there's a bunch of operations. You could see that sitting there in Simula 67. On the other hand, Steve and I felt that the subclass mechanism was not actually going to be helpful for figuring out what it meant to have a data abstraction. And furthermore, Simula 67 had no encapsulation. It was just a mechanism for grouping code and data, but there were no rules about who could access what. The other paper I want to mention is this paper by Jim Morris. Jim was very interested in the ideas of Parnas. So he's saying, there's this idea of modularity. What rules do we have to apply to modules in order to make local reasoning work? And what he said was, well, first of all, it has to be the fact that none of the code on the outside of the module can modify the state that's inside the module. Because obviously, if code on the outside could modify the state, you wouldn't be able to reason about the correctness of the module independently because you wouldn't have control of all the code that could change that state. And then he said, well, furthermore, the code on the outside shouldn't even look at the state. It's not enough to just not modify it, you have to not look at it either, and that's important for modifiability because if the code outside knew what it looked like, then that's part of its interface, and so then you've limited what kind of modifications you can make. And then he went on to say, well, okay, those are the rules. How do I enforce them? And he didn't know how to enforce them, but he proposed what he called seal and unseal. Think of encryption. So the idea is the module has a key. When stuff goes out, it encrypts it. That means nobody on the outside can see it. Nobody on the outside can modify it in a way that wouldn't be detected. So then when it comes inside, you can decrypt it and find out if everything's okay. All right, so this was a very interesting idea. And Steve and I read these papers and some others. And my memory of the summer of 1973 is that it was sunny every day in Cambridge, Massachusetts, because Steve and I used to meet outside for lunch. We would talk about our ideas at lunchtime, then we would separate work independently and meet again the next day. Obviously, wasn't so nice in Cambridge, Massachusetts every day. It just shows you the unreliability of memory. Memory is not really all that reliable. Anyway, Steve and I worked and worked and worked all through that summer, and by the end of that summer, we had written this paper in which we laid out our ideas. We had a notion of what data abstraction was all about. And that paper proposed a pretty modern idea. It said a data abstraction is a set of operations and a set of objects. So it's not enough just to have representations. You have to have the operations too. And then the cardinal rule was that only by calling the operations can you interact with the objects. It also had a sketch of a programming language that would support such a thing. Okay, so now we're in the fall of 1973, and my memory is that in the fall of 1973, 3 first-year graduate students showed up and wanted to work with me. And I was working on this programming language design. Again, this is apparently not true, because I happened to talk to Russ Atkinson recently, and he said, oh, no, it wasn't like that at all. I was his academic advisor. He said, I said to you, I'm trying to figure out what group I should join. I said, why don't you come work with me? So just goes to show you. Anyway, these 3 students and myself, they were the designers of Clue, when Clue was the programming language that went from the notions in that paper to an actual living, breathing programming language. This is a picture. I don't have pictures of my group. I didn't take pictures like that. This is a picture of me in about 1974, and this is Jack Dennis on the other side, just to give you some, some idea. Okay, so it was an obvious next step to do a programming language. I mean, I'd got the idea. Steve and I had developed these vague notions of what a language would be like. Clearly, the next step was to turn those ideas into something real. But I actually had a set of well-thought-out reasons why developing a programming language was the important next step to do. And speaking to students in the audience, it's really a good idea when you do research to have a good idea of why that research is important. So here's why I thought that developing a programming language was important. First of all, I believe that programmers think in terms of programming language constructs. It's how we are. We're building programs, we have certain construct in mind, they're coming out of our programming languages, and so we use them, they color our thinking. So getting data abstraction into a programming language and a construct that programmers could understand was going to be an important step to helping them use this idea in developing their own designs. A second point about building a programming language is it would enable me to answer the question, does this idea really work in practice? Because you see, the idea was that ultimately people were going to build programs in this language. And if they couldn't build the programs they wanted to build sort of conveniently, if they had trouble understanding the concepts, this would be an evidence that things were not working right. So it gave me a sort of a touchdown of reality. A third point was programming languages are mathematical objects, so if you design one, you have to be precise about what you're doing. Now, mind you, in those days, programming languages were described by programming language manuals. These manuals were rather hand-wavy. Often many details were not quite specified. What would happen is the first team that came along and implemented it would make a bunch of decisions. They might not even know they were doing that. There'd be places where things weren't quite specified. They'd decide what that meant. Then the second team would come along, develop another compiler, wouldn't do exactly the same things. There'd be arguments about what is the programming language anyway. Okay, nevertheless, still, this is much more precise than just writing a paper and waving your hands about, here's an idea. And then the final point is that although we may overemphasize the importance of performance in our computer programs, nevertheless, performance really does matter. And it wouldn't have been good enough if the language had been powerful enough that I could build my programs. If they behaved like dogs, people were not going to be interested. So there's a lot of sort of touchstones of reality here. Okay, I'm going to tell you a little bit about Clue, not very much. But I just wanted to mention some facts about it to get started. And in many of these things, you see my reaction to Lisp. Okay, static type checking. Lisp didn't have this. It was so annoying when I was doing my thesis to spend hours debugging and all of a sudden discover, here's the error. If there had been static type checking, it would have been gone, long ago. Heap-based, well, Lisp is heap-based. This was a very controversial decision at the time because those were the days of ALGOL 60 and the academic languages were following that track, and there was a lot of discussion about pointers are evil and so forth. Okay, it turned out to be a very important decision. Separate compilation, that's Lisp again. That's not how programs used to be in the ALGOL stream. You sort of wrote a piece of text. It sort of went on and on and on. And then there were a bunch of stuff I threw out. No concurrency, thank God. Okay, I started off thinking there was going to be concurrency, but fortunately I abandoned that idea. And, even today people are still arguing about what concurrency should be like. No go-tos because I totally bought Dijkstra's arguments. No inheritance because I thought it was going to be a distraction from the main point. Okay, so I'm going to tell you a little bit about Clue, not very much. The way we implemented data abstractions in Clue was through something we called clusters. And the important thing on this slide is actually, so what you see is there's a header, and then there's some internal stuff. And the header lists the names of the operations. So that was a statement about data abstraction. That was saying, here's the operations that you should use in interacting with objects that are implemented by this cluster. The stuff on the inside was hidden. And there's an example of how you call, how you make the calls. And the thing that's interesting here is the use of the dollar sign. So what you see there is we're saying in clue, it's inset has a create operation. Inset has an insert operation. As opposed to what happens in a language like Java, where you will say the object has the operation. This was actually a decision we made in the design of clue. We decided this was a way to go because it would give us binary operations. So you could think about the array type would have operations that worked on arrays. You could pass in two arrays and add them, and you would be sort of inside. I think in retrospect that was a wrong decision. Okay, now we knew even in the paper that Steve and I wrote that we didn't want to have just an integer set. You didn't want to have code that implemented an integer set, and then you'd write another piece of code that wrote a string set and another piece of code that was yet another kind of set. That would be very tedious and annoying. So we knew that we wanted to have polymorphism, or generics. We wanted to have a piece of code that would implement a set. And then you could instantiate it, as I show you on the bottom of the slide, by saying, well, this time I want a set of integers. And then you could instantiate another time, this time I want a set of strings. The problem with polymorphism, the problem that exercised us for probably until 1975 or so, was that when you have a polymorphic definition, it isn't necessarily true that every type makes a reasonable parameter value. Even for sets, you have to have a type that has an equality, a notion of equality. And if you think about a sorted set, then you would want a type that has some notion of less than or equal, and so forth. So the question was, is there a way of enforcing a rule that ensures that when the type is instantiated, the parameter type that you're providing is one that provides what's needed by the definition? And probably in around 1975, we figured out a solution to that, and that was what we called the where clause. So we added to the header of a polymorphic module a where clause that spelled out what operations the parameter type had to have. So here I'm saying, for it's a set, I need an equal operation that takes in two t's and returns a Boolean. As soon as you have this, then of course inside the cluster, I can write code that uses the equal operation, feeling perfectly confident that at runtime, when I'm actually running, that operation will be there. And of course, when I instantiate, the compiler can ensure that the type that's being provided as the actual parameter has the operations that are needed. So it's like two sides of a contract that go together. Okay, so now clue also had iterators. And one of the confusions that happens here is that the names have changed. So I'm going to tell you what we meant by iterators in clue. What happened was we were very worried about how do you write code of the sort I have up on the screen. You know, many types are collections. When you have a collection, you gather together a bunch of elements, it's because you want to do something with them. So you're going to want to print them, you're going to want to add them. You certainly don't want to have to write that code so you pass what you want to do with them inside, because that would make it very ugly. You know, so you wanted to be able to write loops in some sort of clean way. Now, we didn't actually need to extend the language to support that because there are two ways of doing it without any extra mechanism. One of them is you can destroy the collection. So what do I do to iterate over the collection? I remove one element, I remove the second element, I keep on going until all the elements are gone, and that way I can do something for each element in the collection. But that's kind of ugly, and often I'd like to do more than one thing with the collection. So that's kind of ugly code. The other thing you could do is I could turn my set into an index set, you know, so there's the first element, the second element, and so forth. And then I could iterate using integers, all right? That's actually worse than destroying the collection, because what I did was I forced my users to take something simple and make it more complicated. And from a point of view of programming methodology, what you want is you want to encourage your users, your programmers, to do things in the simplest possible way, so that in the end the program structure is as simple as possible. And having some feature of your language that would force them to complicate their abstractions is not desirable. So that's where we were, again, probably around 1975. I took my group of graduate students, And we went to visit Bill Wolfe and Mary Shaw at Carnegie Mellon, and they told us about generators. And generators are what Java calls iterators. They are extra objects. They have methods to get things started, to pick up the next element in the loop, okay? And we said, oh, yeah, that'll give us iteration, but we thought that was pretty ugly. And on the airplane coming home, my student Russ Atkinson invented iterators. Iterators are like procedures. They can yield a result after result after result, and then each time you run the loop, you use another one. This is a use of an iterator. You call it when the loop starts. Each time it yields a result, you run the loop body. When the body's finished, you go right back inside the iterator, picking up right in the control flow where you left off. And then when the iterator has nothing more, it returns, and that terminates the loop. Okay. And one more point about this. So this is like a 90% solution, you know, a well-known engineering trick. Okay, most of the time this is perfectly adequate. It isn't as powerful as generators because I can't, for example, walk over 2 trees and compare their fringes using iterators. But, of course, you can always fall back on other techniques when you need something more complicated. And we had a very efficient implementation because we would take the loop body, the compiler would take the loop body, turn it into a procedure, pass it in as an extra argument to the iterator. Every time you yield, you just call the iterator, so it's very efficient. Okay, so that's all I'm going to talk about Clue. I'm going to pass on that. And so now it's about 1978. So it took us a long time to design and implement this language because we were really innovating in several directions that people hadn't worked on before. And we went through several iterations of the compiler. You know, we started off with a compiler of Clue 0 that implemented a few little pieces of it, and then we implemented the next set in Clue 0 and stuff like that. Anyway, around about 1978, we were finished. And at that point, I stopped to think about what to do next. And one thing I thought about doing was thinking it was commercializing Clue. But in those days, it wasn't easy to do that kind of thing. I mean, today, I could have put it out as freeware on the internet. And, you know, if you start off with a good support, then people join in and it can get better and better. But that just wasn't a possible option in those days. So it would have meant probably leaving academia or convincing one of my students to pick it up and forming a company, and I decided not to do that. So I was looking around for a research project, and I looked around and I saw the internet, you know. So in those days, this is before, you know, what we have today, but there was the ARPANET, and people could do remote login, they could do file transfer, there was email, and people were talking about how nice it would be to build programs that could run on the internet, where you would have a piece of your program running in various places, and they would communicate somehow. But nobody knew how to do that, so I thought, aha, you know, here's a great research topic. And so I jumped into distributed computing, and that has been my primary focus over the last, you know, since about 1980 or so. I also continue an interest in program methodology. What I'm going to do in the rest of the talk is I'm just going to tell you a little bit about something in program methodology. And so here's what happened. In 1987, I was asked to give the keynote at UPSLA. And UPSLA is the main object-oriented programming language conference. And I think it was just the second year that that conference happened. So I decided that this was an opportunity to learn about what had been happening in the object-oriented stream, and starting with Smalltalk and going on through the languages that followed on from that. The interesting thing was, in those days, there was the East Coast and the West Coast in the US. And on the West Coast, they were doing Smalltalk. On the East Coast, we were doing data abstraction. There was my group, and there was the group at Carnegie Mellon. And there wasn't much communication between us. So it was really different from today. So I hadn't been paying much attention to that whole stream of language, and I thought this was a chance to do it. So I went and started reading papers about Smalltalk and its follow-on languages. And I discovered that, of course, these languages are built around the notion of inheritance. And I discovered they were actually using inheritance for two things. There was implementation, which was sort of what it was invented for. You know, I have an implementation, I can extend the implementation a little bit and make use of the code. It's a code reuse mechanism. But it was also being used for type hierarchy, where they were thinking about there's a type that's implemented by a class, and then there's a subclass, and it implements a subtype, where the subtype is supposed to have some relationship behaviorally to the supertype. And what I discovered, I was very interested in type hierarchy, and I discovered by reading the literature that people didn't know what it meant. So I read a paper that said stacks and queues are each subtypes of one another. I mean, I actually said this in the paper, but if you stop and think about it, You think about writing a piece of code that's using a stack, and what it gets instead is a queue. Well, that might be rather surprising because the behavior is actually quite different. So I was thinking about this, and that led me to come up with what came to be called the Liskov substitution principle. And this was my keynote at Uppsala in 1987. And all I said was a sort of a very common sense thing. And I'm thinking about it from the point of view of the code that you write that expects the object of a supertype. Okay, so I said objects of subtypes should behave like those of supertypes if called through supertype methods. So, you write that code, it expects an object of the supertype. Of course, you're using supertype methods. You don't care if a subtype comes in, provided it behaves the way you expect. So that was all I said in that thing. Of course, I didn't call it the Liskov substitution principle. I just, said, here's a way of thinking about programs. What happened was in the 90s, early 90s probably, I got an email from someone saying, can you explain to me if this is the proper interpretation of the Liskov substitution principle? So then I discovered that there were chat groups on the web, and they were arguing about this and so on. Okay. So when I got the Turing Award, one of the things that happened was I stepped back and started to think about what I had done in the early days. I hadn't been paying any attention. I was working in distributed computing. I was perfectly happy there. But I discovered when I started to reflect on it and looked at what had gone on that what had happened from the time I did the work to the time I got the Turing Award is that there had been a real change in the way that programs were written, and that modularity based on abstraction really was the way programs were written. I mean, this was a wonderful thing to discover. And actually, a very telling thing that happened was my husband was online every day looking at all the comments that were coming up on the internet, and one day he discovered this wonderful quote where somebody said, "What did she get the award for? Everybody knows this anyway." Now, I'm sure this wasn't meant in a kindly way. But the truth was, I mean, that was a telling example of how widespread this idea had become. So, this was a wonderful thing to find out. Okay, I'm just going to conclude with a couple of statements about programming. I have a couple of research projects that are interesting to me. The first one is we have a sad state in computer science, if you think about computer science education, because we have the programming languages for experts like Java and C# that are so complicated. They're good languages, they have good modularity mechanisms, but they're so complicated that you really don't want to use them in your introductory programming language course. It takes so long for the students to start the simple things we want them to learn about computational thinking and so forth. So what's been happening is people have been switching to other languages, and a very popular one right now is Python. And Python is really nice when you look at it. I mean, it's got simple syntax, it's kind of nice and clean, comes with a very nice library, good interpretation features, and so forth. Unfortunately, when you get a little deeper into the language, you discover they threw encapsulation out the window, which is really bad for building big programs, And why does it have to be this way? So wouldn't it be nice if we could have a language that you would start teaching in your introductory class? It's simple enough that you can teach it to novices. But then, as they get more sophisticated and start to think about building big programs, and after all, when you build big programs, you work in teams, it doesn't sort of throw good principles out the window. So that's the first challenge. And I think actually this is in some sense it seems very compelling and simple, but I suspect it's a very hard thing to do right. The other one is massively parallel. This is picking out something that Andy said earlier today. They're coming. Massively parallel computers. I mean, I just been working on a problem. We're running on a computer with 32 cores, but we have in-house one with 80 cores, and so forth and so on. And the real problem is people don't know how to write programs that run correctly on these computers. So there's a huge program methodology problem here. If we can figure out what the right methodology is, then maybe there'll be some reasonable programming language support coming along. So I think that's another very important. These are sort of short-term challenges in the areas that are of interest to me. Of course, as you know, computer science is a fascinating field and one that's sort of outward-looking, and more stuff is coming in. It's a wonderful field to be in. And so that's the end of the talk. Thank you very much.